This is the first in a series of videos on the sampling distribution of p-hat, or what we call the sample proportion. And in particular, let's look at a particular type of situation. So let's look that we have a population, and there's some number p, which is the proportion of the population, or the percentage of the population in which we somehow define as a success. An example might be really easy. Let's look at the worldwide population of M&M candies, and let P equal to the proportion which are light brown. Right? Now the key thing about P is a true, since P is a population parameter, P is a true value. So it's a parameter and it's a true value. P could be any. P could be the number of Americans with a criminal record, or it could be the number of high school age students who get a high school degree, or take statistics in high school. Right? So now let's define p hat to be a sample estimate of P. And the easiest way to define p hat is to take a sample and count the number of successes. So p hat would be the number of successes in the sample over the size of the sample. So for example, if you wanted to know an estimate of the number of 20-year-olds who have a high school degree, you would just take a random sample of 20-year-olds and ask them, do you have a high school degree? So let's do that. Let's do p hat is equal to an estimate of number of high school graduates. Among 20-year-olds. So you would take a sample. Let's do an example. Let's take 100. And p hat might be, let's say you had 73 over 100, or 0.73. Then you would estimate, according to your procedure, that 73% of the population of 20-year-olds in the United States had a high school degree. Well, there's some important attributes about p hat, or properties of p hat. The first one is that p hat should be unbiased. Now, there's some assumptions you have to make here. You have to make that you're sure you're taking a random sample from a population, but the expected value of p hat will equal to p. Or another way to say that is mu p hat is equal to p. That is, the mean of the estimator p hat will equal to the true population value. The second thing that's true is if n is large enough, then the estimator P hat will be approximately normal. So these are kind of both intuitive, right? That P hat will be unbiased, and if the sample size is large enough, then P hat will be approximately normal. So here's the note. So whenever we're going to use little n is always the sample size. Now, we use that very common. Now, sometimes we use the word capital N, the symbol capital N, and that's going to be the population size. And that's not used as often. Now, the third property is not so intuitive, but can be shown algebraically, and that sigma P hat. Now, let's make sure we know what sigma P hat is. That's the standard deviation of the estimator. That's the standard deviation of the estimator. Remember, that's a process. P hat. And that's going to equal to the square root of P times 1 minus P over the sample size N. In order to give this some meaning, let's do an example. Let's say you had a jar of marbles. And let's say you had a jar of 1 million marbles. And 20% of them were purple. And you took a random sample of 20 marbles. Let's say of 40 marbles. Then this is what we know. Number one, that P hat, the estimator, would have the following properties. That mu P hat would equal to P or 0.2. In other words, if you took repeated sample after sample after sample, on average you would get an estimate of 20%. That's number one. The second thing we would do is if N is large enough, and 40 is probably large enough, then P hat, the estimator, is approximately normal. It's distributed normally or approximately normal. It's not exactly normal. And the third thing you know is that sigma P hat, let's make sure we know what that is. That is the variability, right, measured by standard deviation of the estimator will equal to the square root of 0.2 times 0.8 over 40. And let's just calculate that on our calculator. That's 0.2 times 0.8 divided by 40, and take the square root of that. And you get about 0.063. So you get a mean of 0.2 and a standard deviation of 0.063. And that's the basic properties of the estimator P hat.